Good afternoon, everyone. This is Elena Vitti, and today we're going to be talking about nanomechanical oscillators, and specifically we're going to be focusing on beams. Beams are a particularly useful thing to start with because they're very simple and found very often. So you can think of things like wires, nanotubes, cantilevers, really any flexible object that extends outward from a fixed base and is free on the other end. So like a diving board, if you want to think of it that way. So an object that is fixed on a wall over here, and over on this side it is free and able to oscillate back and forth. So as mentioned last time, we approximate this as a spring, a massless spring with some mass on the end. Okay, and if we're talking about atoms that are oscillating together, we'll see that this is analogous to two masses with a spring between them. But for today, we're really going to focus on this single mass on a spring beam object. So let's start with a discussion of what this beam would look like. So there's our wall, and I'm going to try to draw a beam coming out from the wall. Okay, and this beam has some thickness. It's hard for me to draw this here, but you can see it has some thickness. Okay, so it's going to have some length L, some width W, and some thickness T. Okay, so the stiffness of this cantilever is given by the equation K is equal to E sub m, and E sub m is a modulus of elasticity, it's a material parameter, times the width times the cube of the thickness divided by 4 times the length cubed. Okay, so that's how we define that stiffness, and of course where that comes in, that K, is we know that the force here is equal to negative Kx is equal to ma, and this is the K that we're talking about, the stiffness of the spring. So now let's look a little bit more closely at what happens with this spring. So let's draw a plot here. On the y-axis, I'm going to plot displacement, and on the x-axis, we're going to plot time. So this is displacement. So we're going to give that, say, x, and the negative direction is minus x. We're assuming we're just going to go in the x direction here. And let's assume here we have our wall that our spring is attached to. Let me switch colors here. And we have a mass that's attached to a spring. Okay, now if we stretch this mass away from the wall, we stretch the spring. So we see some displacement in the x direction. Okay, and if we let go, we know that that mass is going to move down and come towards the wall, and it will reach some minimum of spring compression. And then once that happens, it's going to bounce back. and then it's going to go through the neutral, and it might come back up here. And if we have no other damping forces, if we have no friction, if we have nothing else, let's say we're in a vacuum, this behavior will continue unhindered in this sinusoidal fashion. And pardon my drawing of a sinusoid here, but the idea is that this is a sinusoidal waveform that's going to be drawn in time as that spring is compressed and expanded over and over again without any friction or anything else to damp the oscillation. So this is what we called an undamped system. It oscillates continuously in time, and there's no other forces to slow it down, the motion or the oscillation. So mass times acceleration is equal to negative of the stiffness k times the displacement x. Okay, of course we know in real life that we do have some damping because we have friction, we have other forces, but let's just assume there are none of those for now. All right, so now let's think about the energy of the system. All right, energy. What is energy? Energy is a force applied through a distance. So in our particular case of our spring, let's draw energy on the y-axis. Let's draw displacement on the x-axis. And let's say this is 0, or our neutral spring position. Negative a here is the most negative displacement that the spring is going to experience. Positive a here is going to be the most displacement that the spring is going to experience. So you can sort of imagine, if I can draw this, you can sort of imagine again our ball on a spring, our mass on a spring. This is its initial position, and it might compress to here, or it might expand to here as it oscillates back and forth. And this is our wall, if you will. Okay, so let's think about the energy involved here. So the potential energy, PE, is going to be given by the integral of the force with respect to displacement. So the integral from 0 to x in displacement of f dx, right? Because this ball gains potential energy between the neutral position and whatever other position it gets to as a function of force with respect to the integral of force with respect to displacement. Okay, so if we take this integral, what do we get? Well, if we take that integral, we get 1/2 kx squared, and I encourage you to do this on your own. Make sure that you understand how this happens. So that's our potential energy. Our kinetic energy, we may remember, is given by 1/2 mv squared. So then our total energy of this system is going to be 1/2 kx squared, the potential energy, plus the kinetic energy, 1/2 mv squared. Okay? So if we look at plotting energy, let's plot first the potential energy and then the kinetic energy. So the potential energy is highest at the maximum displacement. Potential energy is highest here, and potential energy is lowest at 0, right? Because at 0, the object is moving the fastest, and it's all kinetic energy at that point. So potential energy looks like this. I'm going to use a different color for kinetic energy. Kinetic energy is the opposite. Kinetic energy is 0 at the maximum displacement areas, because that's where the spring is, where the mass is still, because it's changing from moving in the negative direction to the positive direction, or the other way around. So this is our kinetic energy. This is our kinetic energy plot, and the black line is our potential energy. Okay, so again, you can see the potential energy is highest when the spring is most compressed, and the potential energy is lowest at the 0 neutral location. The kinetic energy is sort of the opposite of that. Okay, now let's consider the probability of where this ball on a spring goes. So what is the probability of finding the ball on a spring? Well, let's look. Well, this defined probability as P of x. So it's a probability with respect to displacement x. B over v, where v is velocity. Okay, so the probability plot here, this is x direction here. This is going to be the probability P of x. Okay, again, this is minus a, the most negative displacement. This is positive a, the most positive displacement. This is the neutral 0. Okay, so the probability is going to look something like this. Okay, so the probability of finding the ball increases as the velocity approaches 0 at negative a and a. So as we're moving towards negative a, what's happening to that velocity? That velocity is getting smaller and smaller until it reaches a, right? Because that's when it moves, its velocity switches to go back the other way. So it approaches 0. So you can see that probability is inversely proportional to velocity. The probability is lowest at x is equal to 0, because this is where the ball is the fastest. It's fully kinetic energy. It's moving the fastest as it moves through that 0 spot. So that's the probability of finding that ball. Okay. All right. So now let's talk a little bit about the frequency of this oscillation, of this moving back and forth. Okay, so the natural or resonance frequency. Okay, so again, we have looked at this. Let's look at it again in time. This is time, this is displacement x. So for an undamped system, we know that this is a sinusoid. Like so. Okay, and we know that force is equal to mass times acceleration is equal to minus kx. So the question that we're asking here really has to do with what is the frequency of this sinusoidal oscillation, right? So what is the period of this sinusoid, or the frequency of that sinusoid, right? So we know that force is equal mass times acceleration, and we also know that acceleration is equal to the second derivative of displacement. So d2x dt2. All right, so that leads us to write that mass times acceleration plus kx is equal to 0. Okay. So all I've done is I've taken mass times acceleration is equal to negative kx, moved that to the other side and got mass times acceleration plus kx is equal to 0. So here's our governing differential equation. Now we know that the solution to this type of differential equation has the form x of t is equal to a cosine of omega t. Okay, that's a known solution for this equation. Well, if we take that known solution, we plug it back in, we end up with, so take this known solution and plug it back into this differential equation, we're going to end up with ma d2x dt, so the second derivative of this x of t, so that's going to end up being negative ma times omega squared cosine of omega t plus k a cosine of omega t. So I've taken the second derivative of the x function and plugged it in here, plus kx, and that's going to be equal to 0. If we divide by a cosine omega t, we're left with a minus m omega squared plus k is equal to 0. And then we can solve for omega. So omega is equal to the square root of k over m. Okay, now omega is related to a parameter that we know well, and that's frequency. So omega is equal to 2 pi f. That's the frequency that we've used so far in this course. So omega is the angular frequency, is given in radians per second. F is given in hertz. Okay. So let's look at the sinusoidal waveform. And remember, it's useful parameters. If we have a sinusoid in time with the x displacement here, so this is what our sine function looks like. Okay, let's remember that the maximum peak that it can reach, A, is its amplitude. Okay, and the period is the distance between two peaks, or distance between two troughs, however you want to look at it. So this is its period, and that's equal to 1 over f, the frequency that we showed in the previous slide. Okay. So now let's look at the difference between this sinusoid that we just talked about and a more realistic system where we have friction and other forces that cause the system to be damped. So what we've looked at so far is a sinusoid that never decays. So this is undamped. Well, the system could be damped, and in that case, we're plotting a very similar plot in time with a displacement x happening here, and the maximum displacement here starts at A, let's say, but as the system oscillates, the amplitude of the oscillations gets smaller and smaller and smaller in time as friction and other forces act upon it. Okay, so this is what we would call a damped system. So instead of, let's say in this situation where the amplitude continues to be constant, this is something like in vacuum. This case would be something like in water, for instance. And we know that water waves tend to die out or dissipate in time. Okay, so that's the difference between a damped and an undamped system. Now, let's look more carefully at the damped system. Okay, the damped system has an additional force, the dampening force, F damp, and that's given by negative BV, where V is the velocity and B is the damping coefficient, which is a constant. Okay, so the force here becomes, the total force becomes mass times acceleration, which is also equal to minus kx minus bv, right? So we have an additional parameter here that has to do with the damping force. And it turns out that the frequency of the damped system is a little bit different. The frequency is given by 1 over 2 pi times the square root of k minus b squared over 4m over m. So the frequency is a little bit less in the case of the damped system. Okay? And finally, the last thing to talk about is forced oscillation. So in the case of forced oscillation, that means we have something that's driving the oscillation. So you can think of maybe a string on a violin when we're causing that string to vibrate by running the bow across the strings continuously. So that's a forced oscillation. So that's an additional force, F drive, let's call it. Okay, so in summary, these are the forces that we have in place. The spring force, F spring, which is negative kx. We have the damping force, F damp. That's equal to negative bv. And we have the driving force, F drive. That's equal to usually a sinusoid, so F naught cosine of 2 pi driving frequency, F drive. Small f drive is the driving frequency, times t. Okay, so these are the three forces that are come into play, and of course they must all follow Newton's laws. F is equal to ma is equal to minus kx, and a is equal to the second derivative with respect to time.